This demonstration shows how to generate electricity. This process is called electromagnetic induction. All I have is a DC galvanometer. A galvanometer is an ammeter which reads with its needle in the middle, and if current comes into this terminal and out of that terminal, the needle moves to the right. If current comes into this terminal and out of that terminal, the needle moves to the left. So depending on the direction of the current flow, the needle will move accordingly. Here I have 200 turns of fine wire, so it's wrapped simply on a plastic tube. So that is a coil of wire. And here is a very strong magnet. So the demonstration goes something like this. If I just hold the coil and I move the magnet inside the coil, and if you watch the galvanometer, we are generating electricity. So the magnet goes in the coil and we generate electricity. So a couple of points. First of all, we only generate electricity when the magnetic flux is passing over the coil. In other words, when we have movement. So when it's moving, we generate electricity. If it's stationary, we don't generate electricity. If we watch the polarity, when I put the magnet in, the needle goes to the left. When I pull the magnet out, the needle goes to the right. I'm going to reverse the polarity of the magnet. All I've got to do is turn it around, and we now have the opposite effect. So by changing the polarity of the magnet, we can change the direction of the induced current. So what is happening is the lines of magnetic flux are cutting through the coil and inducing an electric current in there. So we produce a voltage which passes a current around this circuit, and that's indicated on there. So one other thing, I'm not going to do anything with the coil of wire at the moment, but I'm going to just change what I do with the magnet. If I put this in and out slowly, we don't generate a great deal of electricity. I'm going to try and do it quicker. So the amount of the generated electricity, it's better when I withdraw that. So the amount of generated electricity is greater when the speed is greater. So it's proportional to the velocity. So if we can increase the speed, we can increase the amount of electricity produced. At this point, I'm just going to change to a different coil. This has 200 turns. So if I now use a coil with 400 turns and try and repeat this, so I'm now going end to end on the galvanometer. By increasing the number of turns, we've increased the EMF induced, the voltage produced by the coil, and therefore the current that will flow around. Okay, just let me remove this. If we don't have a closed circuit, so at the moment this is open, an open circuit, you can't see anything. There's no way the needle is going to move because the circuit is open. I will still be producing an EMF in there, but it won't produce a current. So I'm generating the voltage, but it's not producing a current. For a current to flow, there must be a closed circuit. So now the circuit is closed or complete. Now a current will flow again. Okay, so there is a final way that we can increase the size of the induced EMF, the amount of the current that will flow around this circuit. And that would be to use a stronger magnet. And we would be changing the flux density, B. And I can't really show it. I've got a slightly stronger magnet. I'm trying to move it slowly because I'm in danger of damaging the meter by bending the needle on the ends. This is a more powerful magnet. Oops. This is a more powerful magnet, and that generates a greater EMF. So let's just do a very, very high-speed summary. Let's look at the terms we're using. The three requirements to generate electricity, which is electromagnetic induction, you need a coil, a magnet, and movement. Those are the three things. I've said a coil. It will also work with a single conductor, that is just a piece of wire, straight, bent or otherwise, but we tend to talk about a coil because we're talking about how it's generated at a power station. Okay, so that'll do for now. Hopefully you'll get time to get your head around that.